Hello, this is Mrs. Doral. This PowerPoint is about the history of the atom, and you're going to take notes on things, again, that are underlined, or if I star something, just like we did on our last set of notes. Okay, so this is in history class. Why do we have to even know this? Because basically, to know that scientists have really tested theories, you shouldn't just trust everything that everyone says to you, and that they're not just creative dreams, that we actually can prove that there are little things called atoms, and even now, that there are littler things called subatomic particles. This good-looking guy, his name is Democritus, and we don't really have any pictures of him. As you can see, this is a stone, what they call a bust of him, because he lived way back in 440 BC. He was a Greek philosopher, and I think that's a fancy way of saying that he was a thoughtful scientist. He thought about science, he didn't really do science. And he called atoms atomos, which means uncuttable. He was the first one to come up with the idea of an atom. He also claimed that atoms come in a variety of shapes and sizes. Like if it's if something that you have is rough, that it would be literally rough atoms, or if it was a triangle shape, that it would be made out of triangle atoms, which is not what atoms look like. But he did claim that they came in different shapes and sizes, and many people believed him for a long, long time because he was famous philosopher. Here we have John Dalton. He was an English school teacher, and I know it says he must be SMRT. That's a joke. Get it? We didn't spell smart right. Dalton proposed new information about what makes up matter. He's known as the father of the atomic theory. You're going to see on the next slide what his atomic theory is. Here's Dalton's atomic theory. You're going to have to copy down all 4 parts. Some of them are still true and some of them are not. But at the time, this was the first real theory about atoms and what they're made up of and how they act. And so people didn't know whether parts of it were true or false. They just assumed that all of them were true. So first one, all elements, are made up of atoms which are indivisible. That means you can't divide them. All atoms of one element are identical in their masses, so every atom of oxygen would have the same mass. The third one says that atoms of different elements have different masses. All right, so if it's oxygen, it's going to be different from nitrogen. And the fourth one says that atoms combine in small whole number ratios, like 2 to 1, or 3 of these and 2 of these. So they're not any halves, and you won't see any half percentages or anything like that in the periodic table or fractions. They're going to be whole number ratios. You'll see some decimals, but we'll talk about that in a minute. Okay, let's go through and look at each one of these points. Where it says all elements are made up of atoms which are indivisible, at the time you could not divide an atom. But as of World War II, we could split an atom. And so that one became to the point where it's not true. The second one, all atoms of one element are identical in their masses. That is stating, like, if oxygen, I had 2 oxygen atoms, that they'd both be exactly the same mass. And that's not true, because if you look at the periodic table, the number at the bottom, that 16.00032, that's an average mass. And the reason it's an average is because there are different masses of oxygens, but if you add them all up and divide by the number that they are, then it'll average that number. Atoms of different elements have different masses. That is a true statement, and is just something that you need to know as far as oxygen is different from nitrogen, which is different from carbon. And atoms combine in small whole number ratios, that also is true. So there's 2 parts that are now false and 2 parts that are true. There was a scientist named J.J. Thomson, and he just made the discovery of electrons using something called a cathode ray experiment. This cathode ray, this tube, this green tube in this picture, is a lot like a picture tube on an old TV. And he deflected light using a magnetic field, and what he found was this deflection, the negatives were deflected, and he figured there had to be a force there to make the negative electrons move out, and he discovered those electrons by that experiment. Now Thomson has a new model of the atom. As he did this discovery of his electrons, and now he comes in and he's like, okay, Well, now we know electrons are here, so this must be what the atom looks like. It's like plum pudding is what they call it. They call it a plum pudding model where you have this atom, and inside the atom you have all of this positive goo stuff in here, and it's just positive. And what happens to opposites? Opposites attract, and then you have the negative electrons right here. These blue things are negative, and all this other stuff is positive. All this orange and red stuff is positive. So that's what they thought the atom looked like for quite a while, until the next discovery. Now we fast forward to Rutherford and his gold foil experiment, and he took particles of some kind of light, and he shot them at gold foil. And as you can see, some of the particles do go through, but a few of them actually bounce off something solid. He wasn't expecting them to bounce off of anything. He was expecting them just to go straight through. And he actually determined that they bounced off of the nucleus. This would be similar to taking a BB gun and shooting it at a chain link fence. Most of the BBs go straight through, but there's going to be one or two that might hit the fence and bounce back at you or bounce off to the side. And so with this, Rutherford determined that there was something called a nucleus in the atom. Now that Rutherford knows there's a nucleus, he comes up with a new idea of what an atom should look like. He says, let's get rid of that plum pudding model, and he comes up with the idea that the nucleus is in the center of the atom, and you can see that's that red thing right there. And he said outside the nucleus, these electrons float around freely, and you can see the negative electrons in green floating around. And if you notice on the inside, he's got the positives. So he's got positive protons, he's got negative electrons floating around it. So this is now, again, evolving. This is a new idea of the atom. So now we have an atomic model that has protons and it has electrons. But some scientists said there's got to be something more. This man named Chadwick discovers that the nucleus is just too big for protons alone, because protons don't weigh enough for all of this to be protons. So there's got to be something else there. And so he doesn't actually do any experimenting. He just weighs atoms and weighs things and comes up with the idea that there has to be something more that's making this thing heavy. And so he determines that there's a particle in the nucleus, but it doesn't have a charge. It's uncharged. And he calls that a neutron because neutrons are neutral. Okay, let's just recap the things that we've gone over with our discoveries. Democritus proposed atoms, first one to say there was an atom. Dalton determined the atom's properties, and he had his atomic theory. Thomson discovered the electrons with his cathode ray tube. Rutherford discovered the nucleus with his gold foil experiment. And Chadwick discovered neutrons. He really didn't do anything, but he calculated and decided that there was something in there and named it a neutron. Okay, so what do we get out of all this? We know the atom is made of electrons, which have a negative charge, and they're located outside the nucleus. We know that protons are positive, and they're located inside the nucleus. And we know neutrons have no charge, and they're also located inside the nucleus. So I'm going to put a positive proton and a 0 with an N for neutrons. And then I'm going to draw an outside of the atom, and I'm going to draw electrons kind of floating around there. So now we have a new model. I have a prettier picture on the next slide, but just kind of wanted to show you what that looked like. Okay, and so now here's what we would call a newer atomic model. It's actually not our modern one, but it's close. You can see that there's protons in here, and that the little blue ones are neutrons, and then these purple ones floating around the outside are electrons. And they're floating around, and we'll talk about their orbits and what they do and how many there are in a little bit. Okay, let's look at the subatomic particles. If you look at a proton, its actual mass is super teeny tiny. That's to the negative 24th. That's like saying 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 1, 6, 7. That's that small. So when we look Look at its actual mass, it is tiny, but yet we still can weigh that, and has a charge of +1. If you look at a neutron has almost the exact same mass, except for these last two numbers are a little bit different. So if you notice that with a neutron, it's probably just a tiny bit bigger. But let's look at an electron. That's to the -28. That's still 4 more decimal places over, so that's even tinier. So electrons actually are the smallest of these particles. Okay, so I need you to write that down. The electrons are the smallest. And protons and neutrons, real close, but if you look, relative mass, very small. This one's biggest. Protons are almost, they're in between. So basically it goes electron smallest, then proton, then neutron. And you can see their charges are off to the right. Okay, for this last slide, I want you to look at the picture of Comerica Park. Now, if this park, from the outside walls of the building, of the gate, all the way into the field, were an atom, I want you to think, how big would the nucleus be? So take a minute, think about where would you put it. Would it be the infield? Would it be the whole field? How big would it be? Okay, now that you've had a minute to think about it, take a look at it. The nucleus would be the size of a marble on second base. It's so teeny tiny. It's very, very small compared to the whole atom. If the whole park was the atom, teeny tiny marble on second base, but it's so heavy, you can't even pick it up. Why is it so dense? Because that's where all the protons and neutrons are located. And remember, the protons and neutrons are the heaviest part of the atom. So if you have the heaviest parts of the atom in the nucleus, that's going to be the heaviest, even though it's so small in comparison to the rest of the atom. The rest of that park would just be filled with electrons floating around. And I want you to copy that down. So if I haven't started, which I don't think I did, I know it's not underlined, but I do want you to copy it all down. Size of a marble on second base. And I would like you to know why it is so heavy, because that's where all of the protons and neutrons are. Okay, so wrap up these notes and show them to me so I can stamp them. Thank you.